All right, so welcome back, everybody. As I said, when my posts on campus were an individual email I sent to people, due to the rain, I decided not to do the class in person because it might be difficult for some people to commute. Um, but I guess some people either like saw it late or decided to go to the class anyway. But was generally the reasoning was to make sure that those who are need to commute, they can be safe. Anyway, so we're going to start with presenting the papers. Since we kind of changed the format of the class for today, some groups decided not to present today and they're going to instead present on Wednesday. So the first group not going to present today. I think that the other two groups are going to present today. And then if you recall, we are talking about side channels for this week of presentations. And also a quick reminder that your second project is also uploaded and ready, and the due date I think is this weekend. So make sure to kind of work on it. It needs some time. It's also relevant to side channels. So hopefully by listening to these papers and working on the projects, you kind of like get most of the idea about side channels. Generally, the theme of the papers today is kind of various different types of physical side channels. So this one that he's going to present now by group two is some form of, kind of new type of side channels that I explained last time when I was describing different types of side channels. If you remember, I said that, like, the most famous ones are electromagnetic and power. But then there is also a kind of combination of electromagnetic and power with other things, including, for example, audio signals, mixed signals, and so on and so forth, that can create interesting new attacks. And this first paper is kind of like about that. If you remember, I talked about the kind of history of side channels, the Tempest, and the title of this paper is actually indeed talking about Tempest. The other paper is also going to talk about various different types of side channels. So without further ado, guys, take it away, please.
Thank you, Professor. So let me introduce our group. We have Raisen and Yachi, and myself, Shreya, who will be presenting the paper on the Tempest comeback. It's a realistic audio eavesdropping threat on mixed signal SOCs. So as Professor introduced, we were talking about side channel analysis this week, and as you may remember, it's basically EM leakage or sounds or mechanical vibrations that kind of leak into the physical environment around a device. And these can be analyzed using SPA, simple physical analysis, SEA, simple EM analysis, or STA, simple template analysis. And we learned the differential version of that as well. So here we are going to analyze audio signals, and there's two ways to recover data. So one is SCCA, which is side channel cryptographic attack. So recover the cryptographic key that we see over here using SCCA. And this part is referred to as the black data. So we decrypt this ciphertext, which is shown in black, using this key, and we obtain this red data, which is the actual plain data. And using SCCA, we can reconstruct this pretty accurately, regardless of the type of data. It could be an image, it could be text or audio. The other way is Tempest, which is direct leakage of the plain data even without it being encrypted. So there's some subtle differences between the SCCA and Tempest. SCCA is not real time, which means we have to warm up our device. We have to capture the data, and we have to analyze the signals and find some measure to decrypt it. And there could be interference, which is unintended commercial radio or spurious signal that comes into the room where the device is present. It could cause some difficulty because the latest SOCs, which have a dedicated cryptographic engine, they are difficult to attack. And the distance is a bit limited, usually within a few cm. Compared to that, Tempest, which is real time, there's no warm up or cryptographic key recovery required. So essentially, you're just listening in to what the person is saying. And it's pretty robust to interference because the attacker can avoid the interference by altering the tracking frequency to a neighboring signal. We'll look into this later. And it's irrelevant to the cryptography hardware simply because we are directly listening to the audio data and it's not encrypted in any way. And it has a long attack range, which can be increased if the attacker combines the dense signals together. Just to give you a brief introduction, what is Tempest? So Tempest is telecommunications electronics material protected from emanating spurious transmissions. So it's this kind of protocol which in around the 1950s, it was discovered that from the emanations from electronics device, we could reconstruct some intelligible data, and it could also be used to spy on others. And as a result of that, several regulations on EM interference and EM compatibility came in, and there was shielding guidelines to protect equipment against spying. And as a result of that, people thought that the Tempest threat was quite low because of the reduced EM leakage from devices. In this paper, we are exploring if the Tempest threat is still low. There are some architecture trends of mixed signal SoCs, as we see here. In the past, we would have analog, digital, and power circuit separately sitting on the substrate. But as we move towards more miniaturization, the stage that we are now, we have digital, analog, and power circuit all on the same chip. And these have increased the coupling noise. And secondly, we know that synchronous digital circuits, they are all clocked with the same clock, and this causes a strong coupling to the substrate. Thirdly, we have the LDO, which used to be on the power management circuit. It has been changed to the switching regulator, and this gives a 47% increase in battery life. So it's much more beneficial to have it on chip. But the switching regulator also has the problem of strong noise-based EM audio radiation, and compared to that, the LDO would simply dissipate heat. But we have the switching regulator dissipating combining with the audio radiation. So as we see here, if we look at this diagram, we have an analog input output. This you can think of as your audio signal, which is going out of the device. And this is the system clock, the digital clock that I was talking about. And this is the switching regulator. So these three signals are combining with the substrate, and they are causing the substrate coupling. So this audio signal that we see, it's coupled on the single common substrate with the system clock and switching regulator. The signal has certain properties that it's very dense because it's at the frequency interval of the switching regulator. It's wideband from a few megahertz to a few gigahertz, and it's actually static because its center frequencies are not changing with time. It has a long attack range of 10 meters, and it's robust to interferences. And to have a very good coupling, we need to satisfy these two criteria, which is to have carrier coupling, you need to have three signal sources, which is two of them are carriers and one is the baseband signal. And to have strong coupling, we need to have two carrier sources that have enough power to be radiated over a long distance. And as I mentioned before, in digital circuits, we have the clock, which is kind of synchronizing all the elements around the CPU. And the CPU itself. So there's very strong coupling from that signal. And we explored and lecture about streaming channels, which was a Wi-Fi chip where there would be a special pattern seen on when the AES was turned on and the radio was turned on, and the special pattern was propagated and could be recovered. So this is something similar, but without encrypting, it's the audio signal that gets captured. So what is the attack mechanism here? We have the victim making a phone call using their Bluetooth earbuds, and the attacker has done some study on the device. It's a known model of the earbud and its frequencies, so the attacker knows its properties and does not need any direct access to the target device. The attacker captures these EM signals and does some sort of post-processing to listen in on the victim's conversation. But this is in real time with a short delay for the post-processing. So it's not at the SCCA where we are recovering the cryptographic key at the end. The second situation is where the attacker eavesdrops on a conversation in a closed-door meeting. but this conversation is being recorded on a voice recorder. Again, the attacker is familiar with this model of voice recorder and knows how to pick up. And then the carrier modulated audio signal actually has lower attenuation and better obstacle penetrability, so it's able to listen in on closed door conversations. And as we saw before, in the case of interference, the attacker can change to an alternate signal. As you see here, there are several center frequencies, so he can just change to a different signal and still be able to listen in. Now I'll pass on to Raisen.
Okay, so let's shift our focus to validating the Tempest attack in the controlled lab environment. So let's first take a look at the figure on the right. It's a chipset. As we mentioned before, it's a tier 3 chipset, combining all the elements in one chipset. And we just use the analog signal as input, and we use the receiver equipment on the left figure to receive the EM leakage. And there are 3 key aspects we need to mention in this experiment. The first one is we measured the switch regulator, the noise. We compare the noise characteristics of these two, and we found out that the switch regulator noise substantially increases the EM leakages. And the second thing we do is we search for the suspected leakage, and we found out that the USNR is relatively strong. And let me explain what is the USNR. So the USNR is the ratio of the unintentional signal power to the background noise power. So if the USNR is relatively strong, which means that the unintentional signal power is recognizable. And the second we do is we attack from a distance. So we found out that the tone signal is sufficiently recognizable. Just from 25 centimeters to 5 meters, or even more than 5 meters, the tone signal is still recognizable. And then let's bring the Tempest attack out of the lab into the real life environment. So just imagine that when you are making a phone call or holding a secret meeting in a classroom and using your Bluetooth voice recorder or Bluetooth earbuds, you may be being eavesdropped on. The attackers may just be using the devices as was shown in the figure on the left. They're very small and portable, maybe just put them into their bags so they can eavesdrop on you. So what the attackers would do, they would do a lot of preparations before they do this eavesdropping. So as mentioned before, they must learn what your device characteristics are. So they're gonna estimate the frequency parameters using the probe. And also they need to capture the emanated signal according to distance variations to get the attack range. Last but not least, they will use the cooperative reconstruction to increase the attack range. By the way, you may be mentioning that the interference in the real life, but as we mentioned before, the attackers can just easily change to an alternate signal with a different center frequency to avoid this interference in real life. So all of the experiments we're doing is based on the analog signals. So what about we using the digital signals as a workaround to avoid the attack? The answer is the attackers can also easily gather information from your digital input signals, such as those transmitted via I2C in real-world environment, just by using the same receive equipment as we've shown before, the portable one. So the only thing they do differently is a method. They use a different method to reconstruct signals into your original signals, the planned data. So in other words, all incoming and outgoing signals, not only the analog signals, but also digital signals on MSOC are strongly linked if the switching record is used.
Okay, next I will talk some insights. The first one is the vulnerability of digital signals to electromagnetic leakage. As the experiments show that digital signals are susceptible to leakage and can be intercepted and reconstructed. So we revealed that even the short-range electromagnetic leakage from MSOCs can pose a significant security threat. And the second one is the impact of switch regulator on signal leakage. You see, switching voltage regulators in MSOC significantly enhance unwanted electromagnetic emission, making the device more vulnerable to Tempest attacks. And the feasibility of remote signal interception. The successful reconstruction of intelligible information from electromagnetic signals at practical distance suggested that more advanced equipment and techniques, the range of this attack could be extended, increasing the security risk. And the fourth one is the coupling and radiation mechanisms rules. The experiments highlight the roles of coupling and radiation mechanisms on signal leakage, indicating that incoming and outgoing signals on MLCs, both in analog and digital, can be intercepted, posing a threat to a wide range of IoT devices. And the future work we could do, the first one is enhance countermeasure against the electromagnetic leakage. We could exploring on materials part to design some alterations that can minimize electromagnetic emissions. And we could alternative the power supply solutions. We have to balance the trade-off between the speed regulators and LDOs. We want to reduce our unwanted radiation and maintaining the battery life in the meanwhile, and also the device efficiency. So we could also figure some advanced switching regulatory design, exploring some super-free switching techniques and other innovative designs for switch regulators to minimize switch noise and reduce the vulnerability to tempest attacks. And also we could improve our chip design techniques. In long-term solutions, some signal designs, mix the signal designs and SIP approaches could all reduce the substrate coupling and unintentional electromagnetic emissions at the chip design range. And there's some open questions for you to thinking after our presentation. The first one is considering the advancement in Tempest and SCA technologies. What measures can organizations take to protect very sensitive data from this type of MS dropping attacks? And in the context of rapidly evolving MSOC technology and increasing the noise coupling, what are the future challenges to maintain Tempest standards and how to manage this challenge addressed? And given the increased electromagnetic leakage due to the power management circuit like switch regulators, what are the potential implications for device designs and user security? How this can be mitigated? And in light of the ability to conduct a Tempest attacks from a distance, how do you foresee the future of secure communication in sensitive environments like the government and the military facilities? So thanks for your listening and have a nice day.
All right, great. Thank you so much. That was a great presentation, actually. I like the slides and the content. Does anybody have any questions? You can either unmute yourself and ask or put it in the chat and I can read it for you. Yeah, while people are thinking, I think the main takeaway of this paper was, various different components in the system can make things worse, right? So for example, the switching regulators and the way that we are, integrating various different components into one giant chip could cause, additional issues in terms of side channels. And to those of you who are interested in like more circuits and more like, traditional EE contents, actually lots of work has been done on designing integrated circuits such that it leaks less. So for example, the presenters discuss designing new switching regulators or adding other components in order to kind of make sure that it's not leaking. These are actually like very active areas of research. Lots of people looking at problems like this in order to make sure that their systems are not leaking. So yeah, good job on kind of like talking about those things. Any questions from anybody? We good? All right. So thank you guys. Sorry that you had to present it, over Zoom, but I think you did a great job.
Thank you.
All right. So group, I think it should be the fourth paper, right? Let me see. No, third paper. So group 3.
Yeah.
All right,
Okay.
so whenever ready.
Okay, perfect. Let me Do this.
Yeah. So this is just before you guys started, this is another paper on kind of like some form of unique way of using side channels. So essentially at the heart, this paper is about using power side channels. But as these guys can explain, the interesting thing about this paper is kind of a unique way of using on-chip kind of sensors in order to collect the power side channels and then do the traditional way of attacking, cryptography methods using side channels. Another big thing about this paper is, remember I told you for physical side channels, you need to be physically present. You have to have physical proximity to the device. But the one of the key things that kind of this paper and paper similar to this kind of enable is the fact that then we can launch these attacks completely remotely, because essentially all you need to do is hack into the sensor, and then the sensor does the kind of physical proximity for you, and then you collect the information. So details these guys are going to talk about. So please.
All right. Yeah, so my name's Omer and my partner here, Jiahao. Our report is on FPGA-based remote power side channel attacks. So what's the issue here, right? The issue is we were discussing side channel attacks in class here, and obviously by analyzing physical signals that are affected by computing systems, we can infer information about the computation taking place. And this is usually used, as the last group also mentioned, for breaking a cryptographic key. But one of the assumptions that we did make in class was that you have to have physical proximity to the system. That was one of the previous assumptions that was made. And however, remote access to FPGAs has opened up the possibility of remote side channel attacks, which we'll be discussing. So some little background on FPGAs and why they're important for this particular scenario. FPGAs, known as field programmable gate arrays, they're defined by AMD and Xilinx, which is, I think, probably the main sort of player in this field. They're defined as semiconductor devices that are based around a matrix of configurable logic blocks connected via programmable interconnects. So basically, this just means that it's reprogrammable hardware that you can implement new logic on without having to fabricate an entirely new chip. And these are very useful as they're faster and more power efficient than regular processors. However, they're more cost efficient than ASIC. They allow for logic synthesis without having to fabricate a whole new chip, as it can be reprogrammed, as I mentioned. And one new thing which is more applicable here is that they can be accessed remotely, as they're now very common in data centers used for machine learning and cloud computing by companies such as Microsoft and Amazon, who are giving developers remote access to these systems, which opens the door for remote side channel attacks using the FPGA. So as we discussed in class, one common form of side channel attack is a power side channel attack. And this is usually done using an oscilloscope to measure the voltage readings, or to measure certain readings caused by the computation. However, by reprogramming the FPGA, attackers can emulate this by creating an on-chip power monitor using ring oscillators. So as we see at the bottom here, we have a ring oscillator, which is connected to a bunch of counters. And basically what it does is the voltage around the area of the ring oscillator is, the frequency of oscillation is measured as a function of the voltage. So by sort of reversing that, you can use the ring oscillator as a sort of voltmeter. So they observe the power consumption of other modules on the FPGA or on the SoC itself, similar to using an oscilloscope as a voltmeter in that particular application. And then through power analysis, whether it be simple analysis, differential analysis, attackers can recover a cryptographic key fully remotely. And the two main types of attacks that this paper explored were FPGA to FPGA and FPGA to CPU attacks. FPGA to FPGA, as we can see on the top right, they place ring oscillators in different areas on the FPGA fabric and measure the voltage at these areas for different processes happening on the FPGA itself. And FPGA to CPU, this is one that as companies are building more complicated chips where the CPU and FPGA are both connected to the same power supply, you can use these ring oscillators that are placed on the FPGA to actually measure the power consumption of the CPU itself. So it sort of leaks, the side channel attack leaks into the CPU, and you can extract information from there. And this is an example here of a cryptographic key that was recovered using fully remote placements of FPGA ring oscillators.
All right, and I will talk about the solution and confirmation. And next, there has been a lot of work and study of traditional power analysis confirmation. For example, we can mask or hide the power trace of confidential module. However, this will cost more money, especially in case of physical secure system. And also we can hide power signal by insert noise, dumbing operation, and also we can we can isolate the module by amount of unusual logic block, like the picture in a slide. This can prevent any direct communication between attacker and victim module. Secondly, is unique to data center, and data center provider can analyze the list and bit string of incoming and trusted users to detecting ring oscillator and carry chain use and delay line. However, there are legitimate use of ring oscillators such as physical uncountable functions and long delay line look pretty much like long added chains. And furthermore, unlike those, netlist is pretty computational intensive. And finally is do not share FPGA. However, this is an imperfect annotation of resources from users to actual physical FPGA device. And furthermore, this doesn't really solve the problem of the current case. We have a user taking a lot of different IP core from third party. All of them are not necessarily trusting integrating that into their final design, and this still does not solve the problem. Next slide. And then we'll talk about the conclusion and the future work. In conclusion, we show that FPGA fabricate can be used to build multiple different types of on-chip power monitors. These power monitors are able to be programmed on FPGA directly or with no physical proximity directly through software. In these power monitors are able to be used to perform a remote section attack and also the conversion attack. And not only can they be used to attack neighbor logic on same FPGA device, but we also that they can attack another component in FPGA system on chip. And in the future, for the future work, as we're discussing in the lecture, we can add randomness. And fortunately, they also have a exist paper called a power analysis attack countermeasure based on the random execution. And random execution is an innovation technique which is proposed by Shenhua. In this method, the correlation between power trace and operand is mixed up to change the execution of data randomized and dynamic manner. They apply this method on security FPGA against a simple power analysis attack to obtain secret from AES crypto system.
And so some questions that we came up with for further discussion is that one of the current limitations of these side channel attacks is the resolution. As the ring oscillator based voltmeters that we discussed earlier, they can't achieve the same level of precision as a traditional oscilloscope would if you have physical proximity to the system. And so as hardware design improves and maybe people can improve on these ring oscillator based voltmeters, can we expect this performance to improve and for side channel attacks to become more of a threat? Or will these sort of attacks taper off as companies begin to be aware of this new threat and learn to enact some of these countermeasures that Jiahao spoke about?
Yeah. And my discussion point is the temperature impacting remote power side channel attacking on FPGAs. Because we talked about the power signals in FPGA in this paper, and maybe the temperature is also the component, is also the element that maybe will affect the maybe is one of the bugs that the attacker can attack the FPGA.
That's about it. Thank you.
Thank you for your time.
All right, thank you so much. Yeah, this is I personally like this paper a lot because it's kind of can provide a different perspective on you know power side channels attacks, which we always thought that we need to be there to measure it, but this is kind of like providing this additional step. Generally, the idea here is that systems becoming more and more kind of heterogeneous, which means that we're gonna add other things to what we traditionally had as a CPU. So now we have FPGAs and so on and so forth. And then kind of the interesting observation in the paper was that you can have like a power sensors on those FPGA, which was generally just a ring oscillator. And for those of you who are interested to actually know that how the ring oscillators can act as like a power sensor, I definitely recommend you to kind of go and read the paper and see the details there. The authors also provided interesting details on like where they put the sensors, how this actually kind of like real attacks can be applied on RSA and so on and so forth. So there are like lots of details on the actual attack, which if you guys are interested, definitely I recommend you to go and take a look. Okay. All right, let's see if there is any questions from any of these two papers. Great. So in that case, I think, as I said, the first group gonna present it first thing on Monday. So I think I see Kevin here. So you guys just make sure to be ready and prepared from Wednesday. First thing we're gonna do is the presentation for that. Okay. All right. So let's have a 2-minute break, and then I'm gonna start the presentation. Okay. So if you remember, like last part of Wednesday lecture, we start discussing wireless security. As I said, essentially, there are two main problems when we were talking about wireless, and kind of, as I said, wireless is kind of like the last part of the discussion that we had, which, we talked about a device where the sensors, the inputs to the system could be problematic because, the environment is changing. We also talked about kind of like, the problems that the system has to the outside world due to, emanations and side channels in general. Now we also wants to talk about this link between these two devices, right? So this communication link between these two devices, or the information that being sent and received between the multiple devices, this could be also cause for issues. And as I said before, there are two main things that we are worried about: the communication and then generally authentication authorization. Okay. And then in communication, we are worried about, the classic CIA. We also worried about privacy as an issue that we are seeing, because essentially communication means that, you know, an adversary could potentially see you know, the activity of the device. These three things, as I said last time, is mainly kind of like protected by using various forms of cryptography. And as I said, I'm not gonna mainly talk about this in this lecture and in this class. This requires kind of like, you know, proper courses on network security, internet security, and so on and so forth. If you're interested, take a look at things such as TLS, TCP, you know, key management, man in the middle, these kind of things on network security side of things. Same issue happens for integrity. How do we actually ensure that the messages that we send and receive are the same messages that we assume that it's been received? That's also a very interesting problem. And then lastly, the problem of jamming and masking, and how we generally protect our systems against the availability aspects of communication. Also very interesting problems that again we won't discuss in this class. What we will discuss in this lecture is the problems of privacy, specifically things such as device recognition, activity recognition, and fingerprinting. These are not about the actual message, but it's actually about kind of the metadata, the surrounding information of the user. Because these are the things that are not traditionally discussed in any sort of like network security and so on courses. The second problem that we're going to look at is the authentication authorization problem. Again, here, many common cryptography protocols are used. And here, you know, things such as digital signatures and so on being used, which are very interesting and important. There's also kind of like, you know, non-cryptography or ad hoc methods that use some form of location or generally physical attributes of the system in order to kind of do either authentication or authorization. And we're going to talk actually about these things in this class as well, in this lecture. And again, these are kind of non-traditional ways of doing wireless communication. If you're interested in traditional, conventional ways, I definitely recommend you considering taking a course in network security, or just kind of like I'll send you materials for reading a little bit more about this. Okay, so let's actually get into it and let's talk about these. So we're gonna start talking about, you know, various different things. We're gonna talk about device authentication and authorizations. But first, I think we're gonna talk about the privacy issues. And last thing, before jumping into the privacy issue, I want to also talk about web security, which is kind of more of a application layer or the protocol layer of these things. This is also a huge area of research, generally internet security, and how internet is being secured is very, very important. And this is kind of like, you know, divided into kind of the browser security, the code that runs within the browser, and of course the communication protocols and authentication protocols. And again, this is kind of requires a proper course in internet security if you're interested to look at this. But let's talk about things that we do want to emphasize and talk about. So the first thing that we're going to talk about is the privacy issue. Okay. And the reason for this is kind of continues the discussion that we started in this class, and that is, you know, the more sensing, the more computation, the more devices, the more connectivity, great. But kind of the downside of this is privacy, right? Because now what used to be kind of a local system that nobody knows about is becoming something that everybody knows about, right? So think about smart home, your healthcare, like everything is being digitized, and as a result, people can actually tap into your activities in order to extract some information. So the first thing we're going to talk about is behavior fingerprinting, right? So essentially, your behavior as the end user can be potentially revealed by just looking at the communication and generally network activity of your device. For example, you know, an adversary who can see the network activity can tell, you know, can answer questions such as when the device is active, how long has been active for, what commands are being processed, whether there has been some malfunction in the system or not, which kind of apps or you know, application is being used more often, less often, and so on and so forth. And you can kind of think about this as kind of a side channel attacks in some sense, right? So this is kind of like very similar to the way that we discuss, you know, power side channels and so on. In fact, you can even consider this a side channel attack, but it's more of like it has its own names and it has its own group of, you know, class of activities and attacks in. Usually the attack setup looks something like this. This is actually, you know, borrowed from one of the papers that one of the groups going to present next week. So generally think about this as, you know, the internet is kind of this part of the system that's kind of connected to the open world, and then within the, let's say within your smart home environment or whatever environment that you have a bunch of different devices. First of all, you know, your devices using different, you know, technologies such as Wi-Fi or Bluetooth low energy or BLE or ZigBee or any other kind of communication technology, depending on the need and the data rate and power and so on and so forth. And the idea is, you know, the attacker can essentially capture this kind of, you know, information that being sent and received between the devices, or between the device and some form of a gateway, or between the devices and some form of ISP and so on. And usually this starts with some form of a sensor that kind of, you know, get this packets. We usually call that sniffing because it's kind of sniff the packets. And then it requires some form of analysis in order to kind of like understand what these different activities are. And finally, it has some kind of classification or inference you know, step, which kind of trying to detect which activity is which. And then this kind of capture point could be at any of these. One of these devices could be compromised. It could be just a passive device that the attacker kind of implants here. It could be kind of, you know, observed from some distance from this devices and so on and so forth. Different attacks exist in this system. As I said, these are exactly what I just said. It could be hacking into one device, it could be planting a new device, or it could be just eavesdropping. For example, a neighbor, let's say, just eavesdrop on the packets of the target system. So what are the attack examples? The details of this you're going to see in the paper next week. But give you kind of like, you know, a little bit of the background. For example, if we have various different kind of communication modalities such as Wi-Fi, ZigBee, or Bluetooth, the sniffer are going to basically collect you know, different raw samples. This could be, you know, the RSS signals, the strength of the signal of the wireless signals that are being received, or it could be any other kind of modalities. Could be the difference in the voltage, could be many different things. And then based on that, usually there is some form of device authentication going on here. Sorry, device identification going on here. That, first of all, there's significant difference between different technologies like Wi-Fi versus ZigBee. There's also individual differences within devices. Then the second question is, can we kind of detect what device is doing, like what sort of state it has? And again, here really the attack depends on what do we trying to do here? What are we trying to kind of you know, detect the behavior of the user? Are we trying to extract a particular secret? What are we trying to do? It's kind of like these two different states kind of dictated by that. For example, in this particular case, the attacker is interested to know whether the device is on or off, for how long it has been on, for how long it has been off, and so on and so forth. And then based on this, and then using a collection of these different devices, then they can detect the user activity. For example, if the light bulb is on in the bedroom and in the living room, that means something, versus if, you know, there's other devices are on or off, that means another thing. So generally, like, you know, the presence, number of people in the room, and all those things are kind of potentially be extracted using this. And then this could you know, be generalized to other systems, so it doesn't necessarily need to be you know, just smart homes. It could be many other things, as you can see here. It could be Mobile devices, could be industrial control systems, could be IoT devices, could be many, many different things. And generally, all of them, there are kind of three things that is happening: is collecting information from the device, then doing some form of evaluation and analysis, and then doing the application detection, device identification, behavior identification, so on and so forth. Interesting thing here is that there are various ways that you can process this, as I'm going to show you in the next few slides. So what can be monitored, first of all, in this kind of setup? Usually kind of like the network or various different signal related features. The features could be things like packet headers, network flow statistics, communications, and so on and so forth. Different, as I said, different devices, could be computers, IoT devices, industrial control systems, and so on and so forth. There could be other kind of features such as raw IQ samples, the frequency domain, payload, and all those things. The source of the behavior, not necessarily just a network. It could be, as I said, it could be combined with like traditional side channel attacks, or could be like, just network communication. Okay. So generally, these are kind of like, the things that an attacker can tap into. Okay. Then there is kind of like, things that the attacker can also further achieve information. And these are the things that we discussed before. So these are, side channels activities that the attacker can achieve using like CPU activities, power consumption, and so on and so forth. The point here is that the attack does not need to be just stays as if wireless attacks could be combined with kind of in-device side channel attacks that we discussed last week. And then once we have this, we need some form of behavior, analysis. Okay. So, and then interesting thing here again is you don't need to necessarily just rely on one. There could be a combination of various different analysis, various different modalities, and various different devices. All together then results in the behavior identifications. Okay. So the attacker is provided with various different sources of information here in order to launch the attack. So how do we detect this, and how do we launch the attack? If you remember, if I go back here, once we kind of collect these information, then we have kind of a bunch of different options in order to do the analysis. And if you remember when I was talking about side channels, I told you that essentially this becomes a learning or signal processing problem. This is exactly the same, right? So again, just the modality has changed, but again, the goals and the type of signals are exactly the same. As a result, you kind of like, applies very similar methods to kind of do the classification. Specifically, you can use some form of rule-based or symbolic way of doing analysis. You can use statistical approaches, such as, tests, statistical tests, parametric tests, non-parametric tests, and so on and so forth. You can use some form of knowledge-based method based on, previous information about the system. Of course, you can use machine learning and deep learning. That's kind of like the dominant way of doing signal analysis these days. And then this analysis could be either at the time domain, or it could be at the frequency domain, or it could be at some latent feature space, right? So it's something that you extract the features from the raw signal, be it time or frequency, and then do the analysis there. This paper that I kind of like, cited here has a very nice analysis on the statistics of the frequency of various different ways. As you can see, of course, the most popular one is let me see if I can use another color here. The most popular one is machine learning, 46%, and as you can see, kind of significantly improving. Like back in 2005 or so, there wasn't any sort of machine learning based method, but as you can see here, is now the most dominant one. And then kind of the second is some form of statistical analysis and statistical tasks, because these are mainly based on, behavior of the system. And what used to be very dominant in the past is now kind of like getting less and less dominant. A rule base is always there and has always been there. And then other things such as knowledge base and so on and so forth. Another interesting thing is that to kind of give you a nice comparison between various different methods. So the approach rule-based statistical knowledge-based ML or time series, and then the others is kind of like look at various different features of these, such as simplicity, expert knowledge, low resources, data set requires, training time, multidimensional data, and so on and so forth. And again, the reason that I'm putting these here is to kind of like show you that, you know, the status of security analysis in many cases is actually becoming just a signal processing and or machine learning or generally data science, right? So security is, as I said at the beginning of this class, is kind of this very multi-domain, multi and cross stack problem, which you need to understand the kind of the behavior of the system, but at the end of the day, it's kind of close to what you do in your normal world as well, to kind of do detecting characterization of your signal, and same things as you can see here applies here basically. Anyway, so these are kind of like, you know, really not security related. It's more of just general knowledge to know, and other slides for you to kind of just know as your information when you are doing any sort of classification. These are very important, useful things to know. Things like accuracy, precision, recall, true negative, false positive rates, false negative rates, F1 score, and all those things. So this is just for you to know. I think it's important. Any engineer or computer scientist needs to know these basic concepts. So I just put it there for your information. And then again, the current trend in device fingerprinting and you know, device behavior fingerprinting is you know, I'm borrowing this from the paper, and these are kind of like, you know, various different questions that's being asked. For example, what's the application scenario? What sort of device type we are looking at? Whether we're using, you know, rule-based or statistical based or knowledge-based, and so on and so forth. Okay. So I mean, once we are doing the device, you know, behavior fingerprinting, similar question can be asked about the device itself. That if you can, for example, detect which application or what has been done on the device, can I also answer this question of, can I detect which device is this, right? So in other words, can I do what we call device fingerprinting? And the answer to this is yes. And again, device fingerprinting, you might, you know, wonder whether cryptography could be helpful here. And if the answer to that is yes, essentially any sort of authentication method that we use based on cryptography can be used for device fingerprinting. Because consider that, for example, digital signatures that we talked about in week 2, where each device who has access to their secret key can sign a particular message and send it to you. And that's the kind of the proof that this device is the device that it thinks it is, right? But the problem with cryptography methods is that they're complex, they're energy consuming, and they're not lightweight in many different scenarios. So what we can do is that we can, you know, rely on physical attributes of the system in order to do device fingerprinting. So I want to talk about that, the fingerprinting approach that are not necessarily based on cryptography. One of them is what we call RF fingerprinting or radio frequency fingerprinting. The key idea in RF fingerprinting is this, that, you know, devices has physical characteristics that are unique to their own. In this particular case, if you think about kind of like the way that the RF circuit is working, basically you have your kind of CPU or digital baseband. This is your digital word. And then this digital word is translated into the analog word and then to physical signals. This is exactly the, this is exactly the opposite of sensors. If you remember sensors, we had the physical, then we had analog, then we had digital. For something like an RF communication, it's exactly the opposite. We start from digital, we go to the analog, we go to the physical. The interesting thing about this process is that due to the process variations, due to the way that, kind of like your analog signal is translating and so on, there are unique physical characteristics of the device, okay? So for example, these are kind of constellation points of the IQ's imbalance. If you don't know what is IQ, don't worry about it. But if you know, there's kind of like, reference between, the way that we create, modulations. And the interesting thing here is that you will see that essentially there's some form of a distribution going on because of the device being imperfect, and there's device variations. There's a tiny bit of difference between what it should have been versus what it really is. And the interesting thing is, if you actually kind of like plot this for various different devices, same type device, but just same different instances, you will see that these variations slightly differ. Okay, so for example, there's a little bit of different distance between them. There's different change of phase or amplitude and so on and so forth. So essentially, this kind of distribution here that you see is unique to the device. And then this is not just the IQ imbalance. There's many other things. For example, the in-phase amplitude is different. The nonlinear distortion is different, the harmonic distortion is different, the phase noise is different, and so on and so forth. So essentially, if you're familiar with the way that we kind of create an RF receiver or RF transmitters, there are various different steps along the way, and these are kind of circuits that you put, including like a digital to analog converter, to filters, and so on and so forth, mixers, and so on and so forth. And these devices create some unique signatures. And these unique signatures are kind of tied into the physical characteristics of the device. And if you actually understand those and extract those, you will see that these are great as the device fingerprint. Because if I build 100 of these devices, each one will slightly look different than the other. So instead of actually relying on cryptography in order to say that, oh, is this device 1, or is this device 2, or is this device 3, I can basically try to extract this and say that, oh, this is similar to the device 1 that I had in my system. So that's kind of the general idea, okay? So how do we actually do that? So essentially, again, what we do is that we extract those features. Then we feed those features into some form of analysis, signal processing, deep learning, statistical analysis, feature engineering that I talked about. And this will then help us to kind of do device identification, right? So we can say, oh, which device is this? And so on and so forth. And then an interesting thing is that it's not just device identification. Additional things can be done here. For example, we can do abnormal detection and so on and so forth in a system like this. So these are the features to kind of give you an idea of like what features do we use. We either rely on some form of the errors that creates in the system, including the frequency error, the phase error, the amplitude error, the statistics of the noise. We also look into like channel or location specific signals, such as signal strengths, frequency response, and so on and so forth. Hardware imperfections is the figure that I showed you, like phase offset, the imbalance between I and Q samples, the offset, and so on and so forth. And then there is like some persistent features. In general, the key takeaway from this slides that I want to show you is that there are physical layer features from each of these devices when it's trying to send a signal. It could be a Wi-Fi signal, it could be a Bluetooth signal, it could be any sort of wireless signal, that these can be extracted and could be used in order to identify the device. And then, as I said, there could be multiple different standards or modulations, and there are various different attacks and weaknesses in the system as well. But generally, that's kind of like the key idea here, that I can kind of like not rely on cryptography, rely on physical attributes of the system, and still be able to identify the device. Let me give you a case study. Is there any questions before that? All right, so this is actually a paper recently published in our group, and that is using fingerprinting IoT devices. And the reason that I'm actually giving you is to give you kind of idea of like how fingerprinting works, and also kind of connecting this into physical side channels. If you remember, I told you physical side channels could be used for, you know, useful purposes as well. So this is actually one of the examples of that. You know, the authors and so on. It's important. So how our devices are authenticated? Devices are authenticated based on you know, as I said, based on usually some form of cryptography, right? So usually there's some form of a secure protocol that, you know, you send or receive some messages, and you say, for example, let's say in this setup, we have two different devices, TX1 and TX2, and then you have a receiver RX. And then the way this works is that you kind of send and receive some cryptography messages, and that's great. You can say that, oh, this is device A, this is device B, or this is device 1, or this is device 2. But as I said, what we are interested in here is we just want to rely on the physical signals. And by just receiving these physical signals, I want to have this kind of fingerprinting module here that can make a decision about whether this is device 1 or whether this is device 2. So what are the advantages of this? The advantage of this is, as I said before, this is completely eliminating the need for a cryptography module. And cryptography modules, as I said, for lightweight devices requires lots of area, lots of power, lots of computation. But this is just basically say that as the device is sending a regular message, the receiver can kind of like, demodulate and receive that message, and also say which message has been sent by whom. Is it device 1 or is it device 2 or just another device? That's the fundamental question. In this particular paper, the modality that we're going to use is the electromagnetic side channels. But as I said, this could be any other physical signals, like could be any RF signals, could be any features within that RF signals. It could be a Bluetooth signal, it could be Wi-Fi signal. In principle, all of them very, very similar attributes, okay? So this is kind of like the setup, right? So we don't have this. We just want to kind of like send the signals and receive this, and then see whether we can detect it. The added benefit of using EM is that we don't necessarily need an RF module in the system, right? So just the device itself, now that we know about physical side channels like EM, we learned that, the device itself, by just, computing some data, it's generate this unintentional electromagnetic signal. So it doesn't even need an antenna or an RF module. As it's kind of run different things, it can actually create the signal, and this signal can be fingerprinted. So this is kind of added benefit when we are talking about EM. But as I said, it could be just like an RF, antenna, and then here again, the signal could be detected. All right. So how does this work? So essentially, this is based on this basic format. So I'm just talking about the paper itself. So it's kind of extract features from the clock, okay? So what we have observed is, different processors have different clocks. As you run different instructions, you get different kind of like, signals from this. And then this creates, emanations. But the interesting thing is that depending on this clock circuitry, the frequency, if you look at the frequency domain, kind of the distribution of relevant activities in the clock kind of changes from one device to another. What changes if you, for example, consider two different devices, device 1 and device 2? You will see that, for example, the amplitude, the period, and general distribution of these kind of different peaks and amplitudes is changing from one device into another. And then if you think about, how this signal will look like in the frequency domain, for those of you kind of familiar a little bit with signal processing, if you take an FFT from any sort of like periodic signal in the time domain, you will receive a spike in the frequency domain, okay? So a clock inherently is a very, very periodic signal. As a result, you will see a signal in the, a spike in the frequency domain. The interesting thing is that, though, is that kind of like the distribution of this spike that you are getting is directly relevant to the distribution of these time domain signals. So for example, if the amplitude is higher, the period is smaller or lower. If things are changing over time, this will be generated differently. It's kind of following exactly similar pattern here. So the key idea here is this, that, different devices has different clock circuitry, although there might be exactly same type devices, but there's tiny bit of differences between kind of these variables. As a result, the signal we'll be receiving at the frequency domain is slightly different. So we can actually build kind of a classifier that look at these signals here and tries to, fingerprinting and say which device is which. Okay, that's kind of like the key takeaway from this, that each device, clock characteristics create unique emanations in time and of course in frequency. So what's the pipeline? So of course, the pipeline would look like something like this. There will be the signal going in, usually some data collection going on, some pre-processing, then some feature extractions, then some classification. Again, this could be, machine learning, signal processing, statistical, so on and so forth, and then there will be some decision made by the device. Before jumping into the rest, let's have a quick break here and gonna come back and talk about this. Let's have like 4 minutes break. All right, let's continue. So I was going to say that, the goal here is using, physical characteristics of the device to fingerprint to fingerprinting. And the motivation here is that I don't want to use cryptography because cryptography is expensive. So how do we do that? We do the data collection. So we made this fundamental observation that, look, the EM emanations of the clock is unique to the device, so I can use it for actually doing fingerprinting, okay? So first of all, it's kind of to show you some evidence. This is kind of like the signal that you're seeing. What we're really looking at is this kind of clock harmonic here, okay? So this is kind of the signal that you're looking at. And clock itself, since it's a periodic, like rectangular signal, the important things, again, if you know a little bit about signal processing, is that if you take a FFT of a periodic signal that's rectangular, in the frequency domain, you're going to see a train of pulses, okay? You're not going to see one spike, you're going to see multiple spikes. The location of these spikes are at, if this is the T period or TP, the frequency of this first one is 1 over TP. And then the second one would be 1 over, 2 times 1 over TP. And then this one would be 3 times 1 over TP and so on and so forth. So essentially you'll see it at the harmonics of that, okay? And what I'm showing here is that this is time and this is frequency. If you recall, this is called waterfall plot. And this particular one, for example, I'm showing you the nth harmonic. In this case, I think n is 16. So this is the 16 harmonics of the clock. I think the clock itself was at 16 megahertz or something. So this can be 16, should be, I think, 23 or something. And then this is the second harmonics of that. So the one harmonic after. So you see that the difference between here and here is exactly that 16 that I said about. So essentially you see the spikes over and over. And as you can see, the signal also shows you that there's kind of all the other things going on as well, like, activities like this. And these are just noises, okay? And if you remember, I said that generally when you're talking about RF or EM signals, there's always, you have to deal with noises, okay? So these are the signals. So of course you do data collection, using some form of, signal acquisition devices, such as an oscilloscope or software-defined radio. Then you need some sort of signal processing or pre-processing. This includes things such as slicing the signal into smaller windows, then taking, FFT from those windows, and then you're going to end up with something like this. Think about this as kind of a vector that has multiple bins depending on how many points you're taking for your FFT, usually somewhere between 128 to 156 or something like that. And each number is basically kind of an amplitude of this. Okay, so that's kind of like each vector, you're gonna have a vector of numbers. Each one is storing the amplitude of the signal. In order to kind of like remove the amount of noise, we usually do averaging to kind of like, have the average behavior of the device. So instead of like collecting all these different vectors, we just sort of store one average vector. Okay. So now that we have our vector, now it's time for feature extraction. The question is like, what sort of features should we look at, given that, we made this fundamental observation that, clock is unique. In this particular paper, we look at various different things, such as time domain analysis, such as autocorrelation. At the frequency level, we look at the frequency, the width, the ratio between multiple harmonics, and so on and so forth. We also look at more advanced kind of cycle stationarity and other attributes of a signal, generally like a random variable. And again, here where you can borrow more information from the knowledge that you have and exists in signal processing. All right, so once we extract these features, so instead of like featuring this kind of raw vector into your classifier, you extract some features, okay, and then send this feature list to your classifier. Of course, the alternative would have been that you just bypass this feature classification and directly send it to the ML classifier. I'm going to talk about that shortly as well. But for now, we're going to do some feature extraction and then do ML classification. And then we make some decisions based on this. And as I said, you can like not having feature classifier, and then you just can't do feature classification, like feature extraction and classification at the same time. And typically, this is what we use in deep neural networks. The question is, okay, what sort of ML classifiers? And then here, typical answers is neural networks. That's the main one that we use, but it could be also simpler ones, SVM, random forest, things like that, right? So, and then based on that, we're going to basically say that which device it is and which mode it is operating on. We actually run different tests on this. We look at, the impact of noises like temperature, attenuation, non-line of sight, different devices. We also look into the fact that, how robust the system is against spoofing, which means that if there is an adversary trying to mimic this behavior, how successful they are. And then we also look at this in long term, which means that, if you run this for 1 month or so, what will happen to the device and so on. So to kind of give you an idea, these are kind of like that's the sort of devices that you can fingerprint, various different Arduino devices, various different ARM boards. And as you can see, what we are looking at here is kind of whether we can identify same time devices. So for example, if you have 10 same Arduinos, can you say which one is device 1, which one is device 2, and so on and so forth? Also, can you kind of distinguish between different types of devices? Can you say this one is Arduino and this one is an ARM device, or so on and so forth? Or for example, if you buy Arduinos from various different vendors, can you say which one is which? These are all fingerprinting ideas, right? So you can imagine there are a bunch of different ways that you can try to fingerprint the device. And then this is kind of the setup that we use. So essentially you can have an antenna, and this antenna, depending on the modality. Since here this is an EM signal, we use this antenna. If you're using an RF signal, you use another antenna, so on and so forth. This is kind of the results to just give you some idea about how accurate this is. Usually we are talking about like 90% plus accuracy for various different things, but of course you can see things like change in temperature or attenuation and so on could decrease the accuracy of the system. And this is expectable because this is expected because generally we are dealing again with real signals. So you might also think about like what other applications this might have, especially in terms of security. And there are interesting things that we can do with this. Okay, so fingerprinting, of course, the number one use case for fingerprinting is whether I'm talking to device 1 or 2, essentially identifying devices. But let's imagine a scenario like this, that you have a hidden device in your room. Okay, for example, this is typically, say, kind of like an Airbnb scenario where, for example, you go to an Airbnb, you don't know nothing about the room, but you're worried that there might be like a secret microphone or secret camera, or generally any secret, digital device that can record audio, video, or something like that in the room. how can we actually detect these devices? Okay, so one application of like a fingerprinter like this is exactly that. The idea is that any sort of electronic device exists in this room and unintentionally create some signals, right? This could be either some unintentional RF signal if this one is connected to any sort of, wireless communication mechanism, or if it's not connected to anything and just record things locally, it will create some EM emanations, okay? So if I have this kind of method that can reliably detect different kind of devices, although I cannot say which device it is, but I can detect the presence of this device in this room, okay? So consider this as kind of like a mine, finder or metal finder kind of device that people use. This is basically hidden device finder in some sense, right? So that's one use case. So basically the decision is not like, oh, this is device 1 or 2. The decision here is that this is a device that we haven't seen before, right? And then this is definitely an interesting and important security question. The second thing that, this could be used is we can use this in order to detect the state of the device, okay? So whether the device is on or off, whether it's active or idle. These are important questions that is also important because if the device is supposed to be idle but now active, or if the device is supposed to be off or on, but now is on, this is also a security vulnerability. We want to make sure that the device operating the way it's supposed to operate. But this is also another application scenario on top of saying that whether this is device 1 or this is device 2. So for example, we can basically, our fingerprinting module could say, oh, this is device 1 and it's on the active state. Lastly, there are questions such as, the robustness of features and so on. Again, this is depending on the way that you collect the signals, the features that you're extracting, and so on and so forth. I mean, at least for this particular example, we show that, across different times and different temperatures and so on, the system stays robust. But this is a big problem in general for these devices. This kind of will give you some idea of the experimental setup. For example, you can measure it from some distance up to kind of like 10 feet. We can measure this. You can also like measure this in non-line of sight, scenarios. So it doesn't necessarily needs to be kind of like non-line of sight. It could be kind of like behind the wall or something. There's a question. Somebody asked, this type of attacks would not work on devices that are designed with low EMI. Some devices could be also shielded. Yes, exactly. So if, for example, you want to create a hidden microphone or a hidden camera, probably something you want to make sure is your device doesn't leak that much. In practice, though, making devices completely kind of dark in terms of EMI is very hard. You can have a weak EMI signal, which is great. But you cannot have like a 0 EMI. So this really becomes like how you actually deal with like very weak signals. That's kind of like what is happening here. But what we're trying to show here is that it's possible for kind of commodity devices. But if somebody kind of like, puts lots of engineering efforts to kind of reduce the EMI, then of course this method may not work as expected. All right. And then another thing that you might wonder is like, what if you have multiple devices and multiple orientations? This is also something else that we tested, and generally it's important in these scenarios. For example, if you have a bunch of different devices all on at the same time, can we actually detect these kind of things or not? For example, like if you have 3 devices, all of them like, in the line of sight of the device, and we want to identify this, can we do that? And the experiments show that, with good signal processing and good classifications, you can do things like that as well. All right, so that's it for fingerprinting. Is there any questions here? Great. So if you remember at the beginning, I said that, the problems that you're looking at for wireless devices is, first of all, privacy, and that's where we discuss, behavioral fingerprinting and device fingerprinting. Then we talked about, Then we talked about, authentication and authorization. And this is where we again use another application of fingerprinting and show that, fingerprinting can help us to identify devices. And not only that, we can do things such as hidden device detection, state detection, and so on and so forth. And then last thing I want to talk about is, the physical attributes of the system. Can I actually use collection of cryptography and signal processing in order to attribute, to detect some physical attributes of the system? For example, what I've shown so far is I can, for example, tell whether this device is on or off, right? So some information about the device I can tell. But I want to kind of generalize this into other physical attributes, okay? So a specific thing that I'm interested in is distance and generally locationing. Because distance has lots of interesting active impacts and use cases. And actually, I think one of the papers that we're going to discuss next week is going to be about this type of attacks. This is also borrowed from my colleague. So the importance of, proximity and distance is very important. If you think about many application scenarios that we have, think about, for example, contactless payments that we have these days. You kind of like have your card, you put your card next to a kind of a reader, and then, a financial transaction happens, right? And this financial transaction only happens when your card is very close to the POS, right? To the reader. If your card is in your pocket or like, a few meters away, this transaction won't happen. And it's very important that this transaction only happens when you consented, right? Which means that it has to be very close to the POS. So in other words, the distance should be first verified. If the distance is larger than some form of threshold or some form of limit, then this should be blocked, right? Another very important application scenario is kind of like this remote lock. So for example, consider your automobile lock, car doors or truck doors, engine starts and stuff like that. Most of them have some form of like key fob that you have. And then when you put the key fob next to your car or next to your trunk, then it opens the door or to start your machine and so on and so forth. If this key fob is far away, then this device won't work, right? You probably have seen it in many of the cars that automobiles that you've seen. Similar things such as smart locks, key fob that you have for your apartments, screen lock, unlock for your computers, the toll collections, many instances. So as you can see, actually, the importance of verifying that something is close to another device has lots and lots of application and use case scenarios, very important applications, right? Dealing with financial and so on and so forth. So we need to kind of like have mechanisms that can securely and reliably verify that one entity is close to another entity. Okay, so we need this, and that's where this physical attributes, in this case location or distance, is important. We need to develop mechanisms. So we're going to talk about this in the rest of this lecture and probably on Wednesday. So first of all, let's actually talk about an interesting attack. This is what we're going to see in one of the paper presentations next week, and this is what we call relay attacks. I'm not going to talk much about this. You're going to see the details on next week, but to give you just a basic idea, remember I told you that if I have a key fob, okay, if I'm close to the car, then I should be able to unlock the door, right? Or for example, if I have a smart, a credit card or something, I should be able to, if I'm very close to the device, I should be able to pay, right? And if I'm not, then the system is secure. Okay, that's great. And the interesting thing about this relay attack is that the attackers find this interesting and very neat way of kind of proving to this device that the key is actually very close to them. Of course, there are lots of ways of making sure that, you know, this cannot be easily replicated. So the replication is out of the question, because usually in order to replicate a key fob, you need to have the cryptography keys. And, you know, if your cryptography mechanism is secure, then you cannot really replicate that. So you cannot replicate the key, but you can do this very interesting trick that if I have an antenna here that collects the signal, okay, then if I kind of transmit this signal using another antenna to this device here that is close to the car, and then kind of replay this signal to the car, then I can basically kind of lie about the distance. So for example, let's say your car key is in your pocket and you're sitting in your classroom. Your car is parked in the parking garage, for example, on the you know, few hundred feet or even miles away from where you're sitting. But let's assume that there is an attacker sitting next to you in the class. What they can do is that they can trick you to kind of like, you know, send a signal to this device. This device is basically, think about it as a mirror. Basically, all it does is that gets the signal and transmits it further away, far away from the device and close to the car, and then just basically, again, mirrors it from here to the car. The car has no idea whether the signal is a legitimate signal, whether you are really close or this is just the mirror version of the signal. And this is a very interesting, very powerful, and in fact very, very feasible attacks and called relay attacks. Okay, the relay attacks has been, you know, implemented in many different scenarios. I think the paper that we're gonna your colleagues and your classmates gonna talk about is about automobiles, but it's also like a whole bunch of other systems, including like payment systems, you know, key fob systems, and so on and so forth, that there has been lots of attacks there. Okay, so essentially this is kind of like, you know, the general idea of relay is that, you know, we create a communication between two legitimate entities. So again, here we're not replicating this key, or we're not fooling this car. There is like the original key fob and original card still talking to each other, but we are lying about the distance. Okay, so the only thing that we are kind of like changing here is that the key and the card is far away from each other, but we are using this technique in order to kind of lie about distance. So we need to kind of like fix this issue, that not only we need to, you know, have strong cryptography methods, but we also need methods on top of that to kind of verify and enforce distance, so that's, you know, relay attacks won't happen. Okay. So essentially, this is kind of like, you know, the idea of what we call establishing proximity or proving proximity. That, you know, we want to show that, you know, proximity is equal to have an actual physical distance. Okay. And then how do we do that? Essentially, we're going to kind of anchor this into some physical phenomena. Essentially, we're going to say that, you know, if the device is close to something, it has to, you know, follow some specific physical phenomena such that, you know, it's impossible in terms of physics that the signal is further away from something and still can kind of be close. So we kind of like make the proximity and physical distance the same thing. How do we do that? We're going to use this kind of various different features, and generally this is, you know, what we call distance bounding. Okay, so the idea here is this, that, you know, when we are sending a signal, like physical signal, for example, in this case from the car to the from the key to the car, there are a whole bunch of things that, you know, happens. You're sending this physical signals. There are things such as, you know, the path loss, the attenuation, the phase of the signal, the time it takes from the signal to travel, and all those things. And these, excuse me, these physical attributes are actually a function of distance d. Okay, so if we can use this physical attribute, things such as the amplitude of the signal, the phase of the signal, the time it takes to travel this distance, and so on. These things can be used on top of the cryptography in order to ensure that this key is indeed in the distance that it's supposed to. Because if I do the mirroring thing, I can send this, you know, I can, you know, replicate the crypto, Okay, I cannot replicate this distance. Okay, and this is where this kind of distance bounding mechanisms, this defense mechanisms will come into the play. Okay. So for example, as you can see here, if the car, for example, sends a signal and then receives the signal from the key, there will be a difference between the phases that it received, and we can basically measure this phase difference. And then there's a relationship between this phase and this distance. Okay, so basically by measuring phase, I can verify that whether this distance is the same distance that we think it is. Another thing that we can do is what we call time of flight, which means that the time it takes for the signal to go to one direction, or from, you know, round trip from going to the key and coming back from the key. And this is basically limited by speed of law, which we know that, for example, you know, the distance between two elements is the time it takes plus the speed of light. And since the speed of light is kind of limited and it's not changing, I can basically just measure this time and I know the distance. Okay, so these tricks, this physical tricks we're going to use, either one-way time of flight, or two-way time of flight, or the phase-based distance estimation, in order to understand and prove that, you know, a particular instance is either close to another distance or not. Okay, and this is, as I said, this is what we call distance bounding attacks. That, you know, this is the idea that we're going to go after. I'm going to pause here. I'm going to then talk about this, and of course, let me talk about the adversary and then pause. So if you're going to use this, then the main thing is that the adversary can also kind of understand this and try to mimic this. So for example, we can have a relay plus attacks, which not only we kind of like mirror the signals, but try to kind of see if we can somehow lie about this time of flight, or lie about the phase of the signal. Okay, so whatever we do in terms of, you know, fixing this issue of distance should be collection of making sure that these physical properties are maintained, and as well as we need to make sure that the attacker cannot easily replicate this physical characteristics. Okay, and that's where we're going to talk about this this distance bounding mechanism, which is actually a kind of combination of physical attributes and in cryptography. Very neat idea. I'm going to talk about it next time in more details. All right. Any questions? Cool. So then I see you guys hopefully in person on Wednesday. Okay. Thank you.